Hello and welcome to the lesson. Today we're going to have a look at probability for Year 12 AS Maths, and the main focus is on Venn diagrams, which is mentioned in GCSE. So we're going to have a look at this in a bit more depth and think about Venn diagrams, or you might even have 3 circles as well. So before we get going, let's have a look at the warm-up questions. So here they are. I want you to press pause on this screen, or just stop the video and try these on paper on your own. When you're ready to see the answers, press play and just use video solutions to double check you've got them all correct, and if not, make corrections where necessary. Okay, let's have a look then at question 1. Question 1 is fairly straightforward. You've got a grouped frequency table showing to the nearest minute the minutes late of 36 students on a given day of school, and we need to complete the grouped frequency table. So what we're told here is that there's 36 students, and so we know that the sum of all the frequencies therefore has to be 36. So far we've got 16, 10 and 2. So far we've got a total of 16 plus 10 plus 2, which gives us 28. Now the total needs to be 36, so this figure here therefore must be 36 minus 28, which is therefore 8. So just fill this in there. That's all there is to question 1. Question 2, use linear interpolation to estimate the lower quartile of the grouped frequency table in question 1. So just to remind you of what we had for question 1, this is what we had with the value of 8 filled in. Now what we need to do here is to work out the limits on these class intervals. So you need to know that these have been rounded to the nearest minute. And so what we need to do here is to work out the actual boundaries. So at the top, what we'd have is this. 0.5 is the lowest possible value that would round to 1. The absolute cutoff between rounding down to 2 or up to 3, this absolute boundary condition would be 2.5. Similar here, between 4 and 5 we've got 4.5, between 6 and 7, 6.5, and it'd have to be less than 9.5 to have rounded down to 9 and have been in this interval here. Likewise, now what we need to do is a cumulative frequency. So that's what we do here. Actually, the question is easier because it's for lower quartile. We don't need all these numbers, but it's just a good practice to get into whenever you see this word, or 2 words, linear interpolation. So anyway, there's 36 values. Quartile, we need to work out the lower quartile. Quartile sounds like a quarter, so all we do is work out a quarter of 36, a quarter of all the values. So 36 divided by 4 is 9. That tells us that the lower quartile, Q1, has to be the 9th value. The 9th value is obviously within the first 16, so that tells us that Q1 is lurking somewhere in this category here. So it's going to be in the first 16. It's the 9th one, therefore, out of 16. So I can say it's the 9th one out of 16 in the interval from 1 to 2. So therefore our estimate for the lower quartile, Q1, we start where this interval starts, the lowest possible boundary. So we start at 0.5. We're now going to add on 9/16 of this class width. We add on 9/16 because this fraction comes from this description here. The fraction is always what number value it is relative to the interval it's in. So it's a 9th one out of 16 in this particular interval. So we add on 9/16 of this class width. From 0.5 to 2.5, that's a width of 2. So all we need to do now is to work this out and round it to a suitable degree of accuracy. So we get the calculator, type in 0.5 plus 9/16 multiplied by 2, and we can see here that the lower quartile is 1.625. You can leave it like that. 4 sig figs isn't too bad, but I think the general golden rule, if in doubt, round to 3 different figures. So I'm going to call this 1.63. After all, it is an estimate, so it might seem quite peculiar to give your final answer rounded to lots of decimal places. But anyhow, that's our final estimate. The lower quartile would be about 1.63 minutes, or if you wanted to be exact in your estimate, 1.625. Question 3. We have to write down an estimate of a probability that a student selected from the grouped frequency table was more than 1.652 minutes late. So, if you're aware of what we just had from before, here's the table, of course. 1.625, if you remember from question 2, that was the lower quartile. Okay, so what this means is the ninth value, the estimate of our ninth value, was this one here, 1.625. So we can say that 9 values were 1.625 or less. So therefore, the estimate of how many of these were more than this will be the total number of values, which is 36, minus this 9, which is 27 students. So 27 were more than 1.625 minutes late. But just be careful here. It's asking us for a probability. So the probability of a student being more than 1.625 late is the number of students. It's essentially the relative frequency. It's the number of students that were more than 1.625 minutes late, which is 27, out of the total number of students, which is 36. Because it's a probability, we can leave it like this. We can leave it unsimplified, and that's fine. If you want to, you can simplify it down and say it's 3/4. So this is absolutely fine, or if you want to simplify, that's fine too. Then question 4 finally, estimate the probability that a student selected was between 2.5 and 6.5 minutes late. So again, here's the table. Now if you look closely, between 2.5 and 6.5 minutes, it's all of this here. Between 2.5 and 6.5 is just this range in the middle. So it's this 10 students plus this 18. So this probability that they were late between 2.5 and 6.5 minutes is the relative frequency of how many students were between 2.5 and 6.5 minutes late. So 10 plus 8 is 18 over the total number of students, which is 36. And 18 out of 36, if you want again to simplify, that's 1/2. That's the warm-up done, so let's have a look at the main body of the lesson, which is centred on Venn diagrams. So, what about Venn diagrams? Well, a Venn diagram, the first thing which people aren't often taught is who they're named after. No guesses, no prizes for Mr. Venn, or Mrs. Venn, or Miss Venn. It was named after John Venn, who was born in 1834. And these can be used to represent events graphically. So they're very visual and a nice way to represent data where more than one event is happening at once. So frequencies or probabilities can be placed in the regions of a Venn diagram. That's John Venn, that's how he looked in his day. And I'm going to show you now what a typical Venn diagram looks like. So I'll fade him out and fade a Venn diagram in. So this is a Venn diagram representing two generic regions. So every data element belongs inside this rectangle. If this is data set, if this is event A, all events which are event A go in here. If this is event B, all of the items which belong in event B go here. This bit in the middle is the overlap of the two events, and anywhere outside of these two ellipses would represent any value which doesn't have anything to do with event A and event B. So the fancy word for all the values is the sample space. So S is just all the possible values, and the closed curves, the ellipses, represent the events. So notation for Venn diagrams. So if we call one event A and another event B in the sample space S, what would the event A and B together look like, where A and B are happening together? Not A or B, but A and B simultaneously, if you like. What we'd have, it'd be the overlapping region of A and B. It'd be this region here, which I've shaded in red. So this event, in technical language, is called the intersection of A and B. It's where the two circles or two curves intersect each other. It's the overlapping bit. It represents the event that both A and B will occur. And it's given this notation here. So A and B, you can read this as. Now, I always think of fish and chips, maybe because I like fish and chips a bit too much, which is unhealthy. But any self-respecting fish and chip shop has an and, like an n. It has fish and chips like that. So the point I'm getting at is you can think of fish and chips as being F and C together. You have fish and you have chips together. Fish and C. A and B. So this symbol that looks like an N, it's not an N, it's a symbol in its own right. This symbol represents the intersection, which in plain English just means and. What if you had to represent the event of A or B? So you wouldn't bother if it was both of them, just one or the other, or maybe both if you really wanted. So some combination of A or B. What this would be is both circles shaded in together. So all of A would satisfy this, or all of B, as would the middle bit. The event A or B happening would also therefore include A and B as well. If you weren't bothered if you wanted fish or chips, you wouldn't really be too upset if you got both, because then you could take your pick. So it's all of these regions inside the curves. This event is also called the union of event A and B. So it's circle A and circle B, or ellipse or curve. It's both of these unified, in other words, joined together. So this represents the event that either A or B or both will occur. So in fancy language, notation for this is A with this U symbol B. And at this stage, I'm going to abandon my fish and chips analogy. Have a think about it, and you'll get the terrible joke. So U, well, it looks like a U anyway, represents union. In plain language, that just means or. Finally, what if you wanted to represent something which wasn't? So if you wanted to represent the event A, for example, it'd just be the circle A all coloured in. What if you wanted to represent the event of A not happening? Well, what we'd do is shade in everything that wasn't anything to do with A. So it's colouring in everything apart from what it isn't. So this event is called the complement of A. So the complement is everything apart from itself. It represents the event that A does not occur at all. So the technical notation for this is A dashed. And this dash symbol here just represents the word complement, or in plain English, it just represents not. So A dashed just means everything that isn't A. So A and not A put together will equal certainty. If I added together the probability of rolling a 6 on a dice and the probability of rolling non-6, that would always equal 1. A 1/6 chance it's a 6, a 5 in 6 chance, but it's not a 6. So the event A and its complement, or any event in its complement, are linked in this way. So I'm just saying here, please note that the probability that A does not occur is equal to the difference between 1 and the probability that A does occur. So that's one way of writing it here. Probability of A dashed equals 1 minus PA, or we could say that the probability of A, the chance of A happening, plus the probability of event A not happening is equal to 1. That's the way I prefer to write it, but either way is absolutely fine. Let's now have a look at a worked example for these Venn diagrams. This one kicks off without being too difficult. The others are slightly more involved. All we're asked to do here is shade the region A dashed intersection B. So this means A dashed and B together. So this is going to be an overlapping bit. First of all, in red, I'm just going to sketch in what A dashed would be. A dashed means everything apart from A. So A dashed is everything on the outside of A. So it's just all of this here. So that's going to be intersecting with B. Now B is just for circle B. So circle B is all of this. So remember this N looking symbol, the AND, means where one and the other happen at the same time. In terms of this ugly colour coding, it's essentially the region where the overlap is. So whereabouts can you see red and blue? Well, you can see red and blue on this portion of the B circle only. And not this bit here, that's just blue. Not the outside bit, that's just red. And so what we're wanting to colour in is this bit here, the right-hand portion of the circle B. So I'm just going to make that look a bit neater for us. So I'll get rid of all this colour and shade it in looking a bit nicer. So for region A-UB would look something a bit like this. So it's all of this circle B on the right-hand side of itself without the overlapping bit with A. And a bit more there if you want to be a perfectionist. And that'll do. And so that's the region A dashed unified with B. And I want to give you bunch an activity to try. So it's just a simple matching activity, but it does require quite a bit of thought. So the instructions to you are to use your ideas from the worked examples and the notes to match each Venn diagram below to the correct notational description for the shaded region. Fill in which description each diagram matches to by filling in the table at the bottom of the next page in your notes. So my advice would be to use either some jotting paper, some paper to the side of your main notes, or mini whiteboards to deduce each correct region. So sketch it and do some rough work before putting in your final answer. Discuss with your class neighbours to check answers as well. Your extension, if you manage to get to this point, is number 1, to write a worded description for each region. So let's imagine set A is students who like art and set B to be students who like biology. Extension 2 is how many different shaded regions, how many combinations of different shaded regions could there be for this Venn diagram. So my hint to you is think of combinations from the combination side of the course. So what we're thinking of here is the binomial expansion. So pause the video here and try this in groups, or if you're working remotely, try this at home and see how you get on. Play the video to see how they match up together and the explanation of why they match up together. Okay, so press play now if you're ready to see the solutions to the matching activity. So first of all, you've got diagram A, B and C. So diagram A would match to this description B dashed. This one's B dashed because as you can see, everything apart from circle B is filled in. This white region is region B. Everything apart from the white, which is the grey, is not B. It's the complement of B. So B dash just means everything apart from B, which is what this grey region is. In terms of the extension activity, if you got onto this, here's a worded description you may have wanted to write down. Just simply students who don't like biology. B would represent students that do like biology. The complement B dashed is simply students who don't like biology. Diagram B. We've got this shaded region here filled in and just a bit of B that isn't. Now this matches to A joined up with B dashed. It's the union of what A is joined up with what B isn't. So if I colour in what A is just this circle here. You need to remember as well this U symbol means intersection. So U means union, my mistake. U is union. It means the joining together of the regions. So B dashed is going to be everything outside of B. So B dashed includes this bit as well that I've already coloured in. Down here. And all the way over here. So as you can see, the only bit we wouldn't be colouring in is this white region. So this Y, A union B dashed is this one here. In terms of matching this to a description, it could be something like this. You could say students who like art and biology, or neither. So it's essentially those that like art, which is just this bit of the A circle, art and biology, which is middle bit, and neither is this outside grey region. Diagram C, we've just got the overlap of A and B. The overlap is the intersection, so this one's going to go and match with A intersection B, A and B simultaneously. So a description for this one could be something like students who like both art and biology. It's not just art, not just biology, it's both. Next one, diagrams D, E and F. So diagram D would match to this description, A dashed union with B. The possible description for this is it's students who like biology, art and biology, or neither. So for biology students is this B circle, art and biology is this intersection bit, or neither is just this outside section. Diagram E would have matched to this one, A dashed intersection with B. The description for this one could be something like this, students who like biology but not art. And this diagram F, it's everything apart from the intersection of A and B. So it's the intersection of A and B complemented. It's everything apart from A and B. A and B is this bit here. The dash means everything apart from this middle bit. In other words, all of everything else outside of the middle bit. As for a description that matches to this one, something like all students that don't like both art and biology. So anyone that doesn't like both subjects qualifies. If they like one but not the other, that's fine, but they can't be liking both, because liking both is this region here, which hasn't been included. G, H and I. So diagram G, dead easy. This is just circle B, all students who like biology, dead simple. Diagram H, it's the union of circles A and B, but not. So it's everything apart from the union of these two circles A and B. So a description for this could be something like students who like neither art nor biology. They don't like any of them. If you liked art, biology, or any combination of them to be inside of these circles, because we've shaded the outside only, these students can't like any combination of them. I, everything's coloured in. So this would match to B joined up with not B. If you join something up to its complement, that includes everything. Just going back to the probability of event B plus a probability of not event B is always certainty. It includes every possible outcome. It includes every shaded region. So this here, the worded description, it's just all students, simple as. The last three, J, K and L. J is dead easy, it's just circle A, and that's just all the students who like art. K, equally simple, that's just nothing at all. So description 12 is this one. So where would A, which is this bit here, intersect with the event which is not A? So where does event A, which is a red circle, where does that overlap with anything outside of it? It doesn't. A and not A are exclusive from each other. So that's possible. That's impossible, rather. That just can't happen. It's like saying, where does this red overlap with this blue? It doesn't. It's nonsensical. It's an impossibility. So a description for this one, because you've actually coloured in nothing, a description for this one just simply be no students whatsoever, or something to the same effect. No students at all. And this one, last but not least, this one is everything apart from circle A. So this is A dashed, just means not A. A description, students who don't like art. So that's the matching activity and the worded extension. And I want to talk about the extension thinking about combinations of events. Here's how your grid should have been filled in. Okay, so that's it matched on your worksheet. That's how it should look. 7, 2, 10, 6, 8, 3 going down here. On this side, 1, 4, 9, 5, 12, 11. So as I say, second part of the extension. How many different shaded regions could there be for this Venn diagram? So let's think of the different combinations we could have. I'm going to include a table to make this clear for you. So, if you think about it, there's 4 different regions of this Venn diagram. There's just A, there's just B, there's the interlapping region, which is A and B, the intersection, and then there's the outside bit of the rectangle, the edges, which is neither circle. So the first thing to consider is it is possible for of those 4 regions to colour in none of them. So how many ways could we have these 4 regions and colour in none of them? Or we could have 4 regions and colour in just one region. We could have 4 regions and colour in 2, 4 regions and have 3 coloured in, or we could have all 4 out of 4 regions coloured in. So how many ways would there be of having 4 regions and colouring none in? So just a recap for you, how do we do this on a calculator? So where's a combination button? First of all, we type the first number here, then shift, press the divide button, then 0. So 4 choose 0. There's only one way that could happen. The only way it can happen is like this. Okay, just nothing coloured in. There's only one way of not colouring anything in, which is like this. The next one, how many ways would there be of just colouring in one of the 4 regions? So your calculator can tell you this. So what's 4 choose 1? Well, that's 4. So that tells us there's 4 ways of colouring in only one region. So one option would be just this section. We could colour in the intersection, this bit, or we could colour in the outside, like so. So there's 4 different ways of doing that. Finally, sorry, not finally, there's a few more. 4 choose 2. 4 choose 2 gives you 6. And so how many ways are there of shading in 2 out of 4? Well, we could do it this way. That region plus the intersection. This bit and that bit. The outside bit and just this section of the first circle. The whole of the second circle, the bit on its own plus the intersection part, the outside and the intersection, and finally the outside bit and just the part which is the second circle without the intersection part. So that's the 6 ways. 4 choose 3 is the same as 4 choose 1, going back to Pascal's triangle. So 4 choose 1, same as 4 choose 3, so there's going to be 4 ways of doing this. Think of it this way. If we've got 4 regions and we're colouring in 3, we're just having one region which isn't coloured in. So you can essentially just switch the colours. Instead of having one region which is coloured in, imagine different combinations of having a region which is not coloured in. So the outside bit could not be coloured in. That bit might not be coloured in, and the others are. The intersection bit might not be coloured in. Or finally, this part might not be coloured in. And finally, how many ways are there of colouring in every single 4 regions out of 4? There's only one way, which is just to colour in the whole damn thing, which is like that. Now just look here and total them up. How many would you get? That gives a total number of combinations of 16. So for this Venn diagram question, I've done 12 different combinations in the question. I could have had up to 16 to pick from. So that just links nicely to combinations from before. Let's have a look at some exam-style worked examples. So let's see about solving probability problems using Venn diagrams. So question 1, we have a sample of 30 GCSE students who were asked whether they studied art or biology. 7 studied art, 12 studied biology, and 5 studied art and biology. So we asked here to draw a Venn diagram to represent the information. So what we need to do is actually have a Venn diagram ready to use. So here's one I've made earlier. So let's fill this in. So the best thing here is actually to start with the intersection parts. For example, 7 studied art. You can't just do this. This is a mistake, don't copy me. That 7 might be wrong because students here would also be studying art. So does this 7 go here, go there? The answer is right now we don't know. So always start with the overlapping bits, and if there's more than one overlapping bit, pick the overlapping section which is the biggest overlapping bit. So for example, this intersection is just for 2 circles. If there existed an intersection which included parts of 3 different regions, try and do that one first. So based on what I've said, this bit here is a bit of overlap information we've been told. 5 studied both art and biology. Art and biology, that means art and biology. It's this middle bit here, so that's 5. We're told though that 7 students studied art. The art region is all of this ellipse. So 5's already included, we want 7 in total, so we need an extra 2. 2 plus that 5 gives us this 7. On the other hand, 12 students studied biology. Biology is this region here, of which we've already included 5 students. We want a total of 12. What do we add on to 5 to get up to 12? We need to add on an extra 7. Let's double check. 7 plus 5 is 12, that's right. 5 plus 2 is 7, which is right. And 5 in the middle, denoting these that studied both, so we're all okay. But we're not quite finished yet. We have here a total of 30 students. 2 plus 5 plus 7 certainly doesn't add up to 30. So there's a number which is going to be on the outside. So the number on the outside is going to be 30 minus the other numbers we've included. So it's going to be 30 minus 2 minus 5 minus 7. Doing it another way, we might just add these together. 2 plus 5 plus 7, that gives us 14. 30 take away 14 is 16. So we just put 16 somewhere on the outside of these curve regions. If you want to as well, you might want to double check and add them up again. So 16 plus 2 is 18, plus 5 is 23, plus 7 is 30. So we're done. We can now have a look at part B. It says find the probability that a student selected at random from the sample does not study biology. So the ones that do not study biology are anything outside of this B curve. So you've got the 2 here and the 16 here. So it's going to be 2 and the other 16 out of the total number of students, which is 30. So that's going to be 18 out of 30. And if you really want to, you can simplify that down. You don't have to. You can if you want to. That's 3/5. Part 2 does not study art or biology. For ones that don't study art or biology, are all these people outside of the union of A and B. So if we don't study art or biology, we're just left with these ones here, this 16. So that's going to be 16 out of 30. And again, if you want to simplify it down, be my guest. That's 8 over 15. So that's question 1 complete. We can have a look at question 2, which is slightly harder to say the least. So here is question 2. As you can see, it's a case of almost information overload. You've got 80 students in year 12, and it's just a load of information to get through. Just really intimidating. So 20 students study biology, 28 study chemistry, 30 students study physics, 7 study biology and chemistry, 11 study chemistry and physics, 5 study physics and biology, 3 students study all 3. Draw a Venn diagram to represent this information. Well, the thing to know here and to realise, you've got 3 different subjects, so we're going to need 3 different curved regions. 1 for biology, 1 for chemistry, and 1 for physics. And as you can see here, because students do study some combinations of 2 of them, and even all 3, we're going to need these 3 regions to overlap, including the part where all 3 have overlapped, which is going to denote the students that have studied all 3 subjects, of which there are some students. So we need to construct it carefully. I'd suggest it should look something a little bit like this. So I'm just going to show you now what it should look like, something a bit like this one here. So 3 different circles, B, C, and P. Biology, chemistry, physics. Like I've said before, the best thing to do would be to start off with doing the most overlappy, no, that's a word, most overlappy part first. So you've got this region here, which is an overlapping of 2 circles, this bit's an overlapping of 2, this bit's an overlapping of 2, but this very middle bit here is where all 3 overlap. And so if we can do, it's a good idea to start off working out this one first. So this region is going to denote all the students that study all 3 subjects. We are told how many students study all 3, so in this region what we need to do is write in 3. So the first step is this. 3 students study all 3, so we put 3 there. Next up, do the other overlap bits first before doing the separate parts last. So what we could do next is this one, for example. 5 students study both physics and biology. So the physics and biology section is going to be the bit where the B circle overlaps with the P circle. So it's going to be all of this bit here. So if I just put it in blue, there needs to be 5 students in this blue region here. We've got 3 already from this middle bit, the 3 students to study everything, so we need an extra 2 over here, because 3 plus 2 will make the 5 we need. So we add in 2. The next overlap bit to consider is these 11 students that study both chemistry and physics. So chemistry and physics is going to be this bit here, where the C circle overlaps with the P. We've got 3 here already, we need an extra 1 here, so 3 plus what gives us 11. This bit needs to be 8, because 3 plus 8 will give us the 11 it needs to be. The next one, biology and chemistry, is going to be this region here where the B and C circles overlap. So I'm just going to shade this one in here in a different colour. So if we have like pink for this one, and like I said, it's this region here, this region needs to have 7 students inside it, because 7 study both biology and chemistry. We've got 3 here already, so this bit must be the extra 4, like so. Next, it's just a case of adding in all the other bits and pieces we need. So now it says 20 students study biology. So biology is anything inside this B circle here. Okay, so we've got 4, 3 and 2 so far. This total needs to be 20. So over here, what we need is going to be 20, because 20 students study biology, minus 2, 3 and 4. So 20 minus 2 minus 3 minus 4. 20 take 2 take 3 take 4. Well, 2 plus 3 plus 4 is going to be 9. 20 take 9 is going to be 11. So we need an 11 going in here. It then says about students that study chemistry. 28 students study chemistry, so the total number of students in this circle here needs to be 28. We've got 4, 3 and 8 already, so we need a number here, so that when we add it to 4, 3 and 8, it gives us 28. So what we need to do here is 28 for chemistry in total, minus 4, minus 3, minus 8. So 28 minus 4, 3 and 8. Well, 4 plus 3 plus 8 is 15. 28 minus 15 is 13. Okay. Then we need to do the physics bit. So physics is this bottom whole circle. So we've got 30 students that study physics. So already for this physics section, we've got 2, 3 and 8. So the remaining number is going to be this 30 minus 2 minus 3 and minus 8. So 2 plus 3 plus 8 gives us 13. 30 take 13 gives us 17. So that number needs to be 17. We now need to check what this adds up to. We've done all of these regions apart from the one on the outside. If there's 80 students in a college, if it's a sixth form, because it's year 12, it's incredibly unlikely, almost impossible, that all 80 students, if you selected them randomly, would all be science students. Okay, there might be English lit students, there might be language students, BTEC students, you don't know, but it's so unlikely that they'd all be studying biology, chemistry and physics. So there might be some students here which study none of the subjects. So what we need to do here is total up all these numbers carefully. So in this Venn diagram currently, we have 11, we have 13 and 17. So I'm adding up the numbers outside of the overlaps first. So 11, 13 and 17. We also have 2, 3, 4 and 8. So plus 2, plus 3, plus 4, plus 8. That comes to 58. 58 isn't quite at 80. So what's the missing number to take us from 58 to 80? Well, what we need to do here is do 80 minus 58, which gives us the other 22. And so this number on this side is 22. As long as this goes on the outside of these circular regions, you're fine. And so that finally is part A complete. Part B, now we've done the hard work, part B is actually not too hard at all. So part B, it says find the probability that the student studies chemistry but not biology or physics. So if they're studying chemistry but not biology or physics, it's just the chemistry portion on its own, without overlapping with the other sciences. So here was only 13 students that are just chemists without being biologists or physicists. So we've got 13 students which are just chemists out of a total of 80. So the probability of selecting one at random who is just a chemist and nothing else, 13 over 80. Finally, part C. Part C is telling us that we need to find the probability that a student studies chemistry or physics or both. So chemistry or physics or both is going to be the union of chemistry and physics. So chemistry or physics or both is a C circle and the P circle joined together. So the C circle I'm doing here, and the P circle is the bottom one. So imagine it's joining up with this P circle at the bottom. So whatever's within this purple section are all the students that like chemistry, physics, or indeed both. So if we added all these together, we've got 4 plus 3 plus 2 plus 8. Plus 13 and 17. And all of that is out of a total number of 80 students. So if we add up this number on the top, so 4 plus 3 and so on, 4 plus 3 plus 2 plus 8 plus 13 plus 17, that gives us a total of 47. And so this one here is 47 students out of 80 that like any combination of chemistry or physics. So part B is this, part C is that. And that finally, with a bit of work, is question 2 completed. Finally, to finish off, we've got worked example 3. So it says here we have a Venn diagram showing the probability that students at sixth form study maths or physics or history. So it says given the probability that a student studies maths is 0.38, work out P and Q. So these numbers here show probabilities. So the total of these needs to add up to 1. Okay? So the sum of all these numbers needs to add up to 1. So that's the first thing I'm going to do here. So 0.32 plus P plus Q plus 0.07 plus 0.13 plus 0.1, that adds up to 1. So we need to simplify this, which we can do fairly easily. So 0.32 plus 0.07 plus 0.13 plus 0.1, that comes to 0.62. And so P plus Q plus 0.62 equals 1. If we then subtract 0.62 from both sides, we see that P plus Q needs to add up to 1 minus 0.62, which is 0.38. Now what we can do, we can use information we've been given. The probability that a student studies maths is 0.38. Okay, so all that's saying is the total number of students that lie inside this maths circle, well, the total of this probability needs to be 0.38. So from that, what we can say is that 0.32 plus P needs to be 0.38. And from that, we can just subtract 0.32 from both sides. So P is 0.38 minus 0.32, which gives us 0.06. Then Q, we can use this here. So we know that P plus Q is 0.38, and so what we can do is just substitute this into here. So if we sub that P is 0.06, this is now going to become 0.06. So 0.06 is what Q is, so it becomes P plus 0.06 equals 0.38. Therefore, if we subtract 0.06 from both sides, we see that Q is, as well as this number here, Q is also 0.32. Always worth, if you can, double checking your answer. So how can we double check these figures? I'd suggest that we do that by adding them all up and make sure we get to 1. So, if it is true that P is 0.32 and Q, sorry, that Q is 0.32 and P is 0.06, then this 0.32 plus P, so plus 0.06, plus Q, which is 0.32, plus 0.07, plus 0.13, plus 0.1. That does indeed give us 1. So that sort of goes some way to proving that our answer makes sense and is likely to be right, and it is. So now it's over to you to try some of these independently for your independent study. So what I want you to do in the books, turn to page 74 and 75, it's exercise 5b, and attempt questions 3 through to question 7. Okay, so there's 5 questions there to have a go at. You know the drill by now. If you're getting stuck, consult the answers at the back. If that doesn't suffice, have a look at the model solutions. If you're still stuck, ask a peer, and of course, as your last resort, please, as ever, do ask me, either on an email or on the comment section of the videos, ask on Teams if you'd like, or just ask me in person, which by 2021 standards, that's considered old school. But, you know, I quite like speaking in person if it's safe. Thanks again for listening. Do consider subscribing, and I'll hope to see you all very soon indeed. Take care, and goodbye for now.